I remember when I was a student and I used to do these curve sketching questions, I used to really like them. And you're going to be like, duh, it's because you're a math nerd. And you are not wrong. But the reason why I like them so much is because when you do all of the analysis and you actually start to sketch it, it's really cool because you're linking the algebra to the actual graphical concept. And you can see visually what your algebra looks like. And that's kind of really neat. And so what I'm going to show you in this last video, because this is our last Unit 8 video, is just how to put all of that analysis together. And there are going to be 7 steps. So this is a huge question, and it could be just, here's a function, give me the full details, and then graph it. That could be like a quiz. They could give you the one function and just say, do the entire analysis. It is worth so many marks. And so what I'm going to do is break this video up into 2 so that you see 2 different examples, although they're pretty much the same, just one's a little bit harder. Okay, so let's get into it. Here's the first thing that I would be looking for in terms of my analysis. They're going to give you f at x. They have to, because you're obviously going to be sketching it. Now what you might want to do is initially find the first derivative and the second derivative. The first derivative you're going to need because you're going to analyze your local extrema. You're going to need your second derivative because you're going to probably be analyzing your points of inflection. So I'm going to talk about those in about 2 seconds. But first, I do want to talk about the asymptotes. So your asymptotes, you want to do an analysis of your vertical, horizontal, and oblique asymptotes. So around those asymptotes, how is the function itself behaving? So you're going to do an analysis of the behavior and see just what's going on, because that's going to, again, help you to visualize what your function looks like. Okay, so here we come to our first derivative, which is our local extrema. Doing the first derivative and analyzing those results are going to tell you about your maximum and minimum points, and then also about any intervals of increase and decrease. Analyzing your second derivative is going to tell you about your points of inflection. So also any of your intervals of concavity. Now we could add some extra points such as your x and y intercepts. When you have your x-intercept and y-intercept, those are like super easy points that you can calculate. I mean, like your x-intercept has a 0 for the y. Your y-intercept has a 0 for the x. Those are simple points that will help you anchor your function onto the grid. Okay, so those are extra details. That's pretty much enough in order to create a pretty decent sketch. And so you would take all of the things that you know, maybe put it into a legend, because like, to be honest, when you're doing all of this analysis, your work is everywhere. So every time you find something, you might want to like put that answer aside so that you have all of your answers in one place. And then you can take a look at all of your answers and make a pretty decent sketch. And at the end, you might want to talk a little bit more about the domain and range. After you have like your entire function in front of you, you can be like, okay, now I see everything. Now I can tell you a little bit more about the domain and range. Okay, so here we go. Example number 1, and obviously there's only one example. They're going to give us a function. Notice that it's just like a regular rational function. And they're going to ask us, give me a detailed analysis and sketch it. So as I find things, what I'm going to do, and I'm sorry to jump around, is I'm going to immediately put them into the graph so that you can see as we go the building of this function. Okay, so like I said, number 1 step, I'll probably want to find the first and second derivative. Don't ask me how I did it. We've already gone over derivatives, and so I would expect that you guys already know how to do that. Just know that we're going to need them. Going into step number 2, we're going to start analyzing the asymptotes. So the easiest one to find first is your vertical asymptote, which we always look at the denominator for. Okay, so I'm going to scroll down a bit. The denominator can't equal to 0. And so if I start to solve for x, I'm going to bring this guy to the other side, square root both sides. I notice that x can't be positive 1 or negative 1 because it'll give me a denominator of 0. So those give way to my vertical asymptotes. And I also want to just check the behaviors of the original function around those asymptotes. So I have a -1 asymptote right here, and checking from the left and from the right. I also have my +1 asymptotes, and checking from the left and the right. And when you're checking, you're picking a number that's super close to that number from the left or the right, and you're subbing it into the original blue function. Okay, so you want to know how do those numbers behave in the original blue function. And so the answers are right here. -infinity, positive, negative, positive. Before we go on, let's just put all of that into our graph right away. Okay, so I'm going to jump ahead to, is it this slide? Yeah, it is this slide. And the very first thing I'm going to do is I'm going to put in those vertical asymptotes. Okay, so I have one right here, and I have another one right there. Okay, and I'm going to keep those nice and color-coded so that we don't forget. And then I also want to write down my formulas. So the equations of those asymptotes, x equals to -1 and x equals to +1. So there we go. I've actually placed in my legend, remember how I told you like you're going to find a lot of answers, and so just put them all in one place and you'll have them to be able to graph. So analyzing my -1 asymptote, from the left-hand side was going towards -infinity, and from the right was going towards +infinity. The other vertical asymptote, same thing. From the left was -infinity, from the right was +infinity. So as you can see, like we actually don't have enough information to be able to fill out the rest of the graph. And so we need to do further analysis to get like a better look. I mean, like who knows what the middle part of the graph looks like. So continuing on with our asymptotes, I noticed that there was an oblique asymptote. The reason why that was is because if this was like your original function, this is f at x. Okay, notice that your top degree is larger than your bottom degree, which means I can do polynomial division. Okay, so you can see on the left-hand side that I started to do the polynomial division. I got a remainder. This was my quotient, and this is my divisor, and that's my polynomial. So putting that into the function where I have my quotient plus my remainder over my divisor, I can then do the limits because I want to test from negative and positive infinity the behaviors of the oblique asymptote. So from the left and the right of, sorry, not the left and the right, the positive and negative infinities, you'll start to see that this will become 0. And the only one that's really important is this guy right here, which will become our oblique asymptote. So our oblique asymptote is y equals to x. This is the equation that our function can't touch. But how does our function behave around that? So here is the analysis of the behavior. I'm going to start to sub in random numbers for x, something that is close to -infinity and something that's close to +infinity. So I just chose like super big positive and negative numbers. Now, if you're choosing an x value of -100, then your oblique asymptote is going to be at -100. Your function, though, if you take -100 and sub it into your function, is actually slightly below. Okay, like that number is smaller than this other number. Whereas if I put 100 in, well, your oblique asymptote is going to be at +100. If I sub it into my f at x, though, the 100 is going to be slightly larger. So it's actually going to be above the 100. So let's put that into our graph and see what we kind of have. Okay, so first of all, I'm going to draw y equals to x. So going to my function's graph, okay, I'm going to have like another line. And it's going to go diagonally. Oh, this is going to be a little bit tricky. I'm going to start from here. Is that straight? Kinda. There we go. Okay, something like that. And I'm going to extend it. there's like kids screaming outside my classroom. I kind of want to be one of those teachers that's like, go away, go home. But I'm going to be nice. Why am I always nice? I don't know. We'll see how loud they get. Okay, so we have that piece of information right here. And again, we analyzed as it got to negative 100, so into this part of the graph. We went towards being lower than our oblique asymptote. And as we got towards 100 on our x, like positive 100, we were above the asymptote. So somewhere like that. Okay, so you're starting to see a little bit more information about the graph. Let's continue our analysis now. We're on to step 3. The local extrema is talking about the first derivative. And so we have our first derivative, and we're going to start to analyze it. Make it equal to 0 so that you can find your critical values. Now, we do have to take a look at the denominator because they might give us some extra information about vertical asymptotes, although it kind of looks like they gave us the exact same asymptotes. So at least we ruled out that we're pretty much correct about our vertical asymptotes. Finding your critical values means just taking a look at the numerator. So x squared, and then in brackets x squared minus 3 equals to 0. You're going to start to break that up. This is going to equal to 0, and this is going to equal to 0. Solve for your x, and those are going to be your critical values. So it looks like we have 1, 2, and 3. All right, so that's great. That means that we have maxes or mins at those specific x values. But how do we know if they're maxes, and how do we know if they're mins? That's why you actually have to do increase and decrease interval charts. Okay, so what we have here is our leftmost x critical value, which was the negative 1.73. So we're going to put that here and here. So negative infinity all the way up to our first critical number. And then we also have to add in, and we can't forget this, any of the vertical asymptotes as well. We want to see what's going on there. It's not like we're going to have a max or min, but those are still considered critical values. So we put them in right here and here. Okay, now our next critical value, I believe, I'm sorry for scrolling down a little bit too fast, right here is 0. So we got our 0 all the way to positive 1, which was our vertical asymptote. And then our very last critical number, which is the next in line, all the way to infinity. Okay? So testing numbers inside your f prime is going to give you positive, negative, 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 positive. All of that tells you, the first derivative tells you about your slopes. And so you are increasing because you have a positive slope in the first region. You're decreasing in the second region, continuing to decrease all the way up until the very last region, which you then have a positive slope, and that means you're increasing again. So it gives you a picture of what your graph will start to look like. Okay, now any of the parts where you're going increasing and then decreasing, you're going to have a max. And we can actually figure out what that max is. We can take this number and plug it back into your function. Okay, so I'll show you that this is our very first point that we're going to have on our graph. You'll also have another point. Here's like a local min because you're decreasing and then increasing. So at this point, you're going to have a minimum. And we can figure out what that point is by taking 1.73 and subbing it into, again, our function. So we're going to get something like this. We can also talk about the intervals of increase and decrease by just, see now I've scribbled everywhere. Just taking a look at where there's positives and then where there's negatives are going to be our increases and decreases. All of them are going to be round brackets because at any point you're going to either have an asymptote or you're not going to be increasing or decreasing because you would have a slope of 0 at the top and bottom of those max and mins. So now that we have this information, why don't we just start to put that into the function as well? Okay, so here was our graph. Notice that I already have the max and min off to the side right here. Let's put those guys in. Okay, let's see. Max at negative 1.73 and 2. Whoop, I just made a mistake. 2.6. Maybe like, I don't know, somewhere there. Okay, would be our max. That makes sense. I mean, like, doesn't it kind of look like, there you go. Looks kind of like a max, right? And then we have a min, let's see, at 1.7 and 2.6. So maybe somewhere around here. And again, that does look like a min because these guys will start to connect. Hey, okay. All right. And I want you guys to understand that this is like an increasing and then a decreasing. Those are the intervals of increase and decrease that we were analyzing in each of these situations. Okay, just like here would be a decrease and then an increase. That's what we did that table for. It just shows and puts together everything that we see algebraically with what we see visually. All right, now that middle section is kind of weird. It's still not finished, so let's do one of the last parts of our analysis, which is the point of inflection. So doing a second derivative and the analysis is pretty much the same as the local extrema. Taking a look and seeing if we see any vertical asymptotes. And again, we're seeing the exact same ones repetitively. So that's good. That kind of confirms what we've learned. Taking a look at just the numerator and when it equals to 0, you're going to break it up and say this guy equals to 0, and then this one is also going to equal to 0. So the first one we can solve x equals to 0, that's fine. But the second one, you can't really square root a negative number, so I'm just going to get rid of this. That's not going to give us any answers. Now, that should be a point of inflection, but what does a graph look like around that point of inflection? Because remember, the point of inflection is where we have a change in concavity. And so doing a concavity interval chart will give us a little bit more information. And you also have to add in those asymptote numbers. So the critical numbers here are 0, -1, and +1. Okay, so you can see I have them in my chart with round brackets around them. I'm going to test them in my second derivative function to see where it's going to be concave up and concave down. So it looks like concave down in the first and third regions, and then also concave up in the second and the fourth regions. Now, since this guy, let me just show you, we're going from a concave up to a concave down. Right in the middle there, that's going to be a point of inflection. So I can find out what that actual point is by taking the 0 for my x and subbing it into my original function. So that's going to give me another key point on my graph. All right, and then again, obviously we can conclude about our concave up and concave downness. Let's add in that extra point into our graph. Okay, so here is my last, well, not my last, but my second last key piece of information, which is a point of inflection, and that is at 0, 0. Okay, so check it out. You are going from a concave up, because that looks like half of an up, to half of a down. Ta-da! And that's our graph. We can have extra information if we need, so look at step number 5. We could have found our intercepts, and so both of our intercepts seem to be saying the same as our point of inflection, which is 0, 0, which is right here. Yes, I know that the function actually goes through your oblique asymptote, and sometimes it can. Sometimes you'll find that with your horizontal asymptotes or your oblique asymptotes, they might cross over that asymptote, and that's okay. The only thing you want to be really concerned about is how does your function behave around the ends of those asymptotes, not somewhere in the middle. All right, and so the very last step, now that we have our beautiful graph and we see everything that we worked so hard at trying to find placed into its correct places, you have your domain and range. Okay, so obviously your domain, all your x values, not including any of your asymptotes, and then the range, all of your y values, obviously not including any of your asymptotes. But I don't think we had a horizontal asymptote. So we're good. See? Very satisfying. Isn't it beautiful? Like, look at all these colors. It's gorgeous. I have no idea how many marks that would be. It is crazy the amount of marks that this entire process would be. Okay, so try to remember your 7 steps. Try to remember to, as you find each one, place it into a diagram. I mean, if you want, just do the analysis first and then make a legend and then place everything into a diagram. Up to you. It is your choice. So let's go into the second video and we'll try another example.